Hey, welcome back. We've been talking through major ideas for a physics course and as a foundation for an AP physics course, and we're currently finishing up our unit on vibrations and waves. So today we're going to be talking about diffraction in two parts. I'm going to talk you through the major ideas first, and then we're going to get into how to solve problems with the double slit experiment and using diffraction equations. All right, so let's go ahead and get to it. I do want to point out that you have an image of diffraction right here. It's not a very strong one because the wave action is very minimal here. So if you had a little stronger waves, you would see the effect more, but you can still see the effect. So check this out. Waves are passing through this narrow opening and they're getting diffracted as they go through. That means they're bending as they go around that narrow opening or around a corner, you could say, which is pretty amazing. This is a property of waves that is not a property of particles. So let's say there was a swimmer who was able to stand out here and he was being thrown beach balls by his buddy and he was just throwing beach balls. Zoom, that way, just repeatedly kept throwing beach balls like this. Those beach balls, as they go through, would just move in a straight line path, affected by gravity and some of the wave action, but for the most part, they're going to move in more or less a straight line because they're particles. They are like objects. They're not thought of or treated as waves as normal everyday objects. But this is crazy because waves, as they pass through, they will diverge from their original path and curve as they go through narrow openings or travel around corners. And that's what we mean by diffraction, this bending of waves from their original direction as they go through narrow openings or around corners. So it's a property of waves. It's not a property of particles, although we can talk more about what happens with particles later. So this is the property of waves, and it's an interesting one that we need to learn about. So let's get to it. The first thing I want to mention is that you can have a wave source. And if you have a wave source, that's something that's going to be vibrating, or you could have a wave source that is just like one drop of water, and that drop flies back up again, and you get a residual drop that flies back up and down again. So you can have repeating waves or like a pulse wave, but either way you have that, if you're dealing with, say, water, it's going to travel around in a three-dimensional path in concentric circles that will spread out, and the energy will dissipate over time and distance as those waves spread out. So a source of a wave could be a drop of water, let's say, but when I say a wave source, I mean something that's going to radiate out in three-dimensional concentric circles. Alright, well, if you think about the picture I just showed you and think about, alright, there could be wave fronts coming in and then they hit a narrow opening, kind of like this diagram over here. So if you have wave fronts coming in, there's a narrow opening, you can get waves that diffract out. And if the opening is very narrow compared to the wavelength of the wave, then it will behave almost as if it's a source. It will have a reduced amount of energy because only some amount of energy can pass through this narrow opening. But it is important and interesting to note that it's acting as if this is now a source, like someone is just tapping the surface of water or something like that. You get these concentric rings of waves that spread out right here. And this is just through diffraction. Alright, and there are a couple other things that I need to remind you of so that I know that you understand what I'm talking about when I use these terms. First of all, you have the blue wave and the green wave passing each other. There is both constructive and destructive interference going on. And so when the waves are in phase with each other, meaning when the green wave is more or less on top of the blue wave, you have constructive interference going on. You even have constructive interference going on with the troughs. When both troughs are lined up, that's still constructive interference because you're still getting a greater amplitude than either of the waves had going into that or creating that situation. The destructive interference is when the amplitude is smaller, and it would be complete destructive if it is a flat line. And that would be exactly when the crest of the blue wave is at the trough of the green wave and vice versa. Alright, well, I do want to point out that you can have this scenario even if they're moving in the same direction as well. So you can have two waves. Notice they're the same wavelength or the same frequency, moving at the same speed. And if they are essentially on top of each other, then they are said to be in phase with each other. And as they move in phase together, their amplitude is going to be greater as a result. The resulting wave is going to have constructive interference going on. So when I say in phase, I'm talking about two waves that have the same wavelength, amplitude, wave speed, are moving in the same direction and are lined up exactly with each other. So like the crest lines up with the crest of the other wave, the trough of one wave lines up with the trough of the other wave. Now imagine we take this wave and we just shift this sine wave over by half a wavelength, and you would get this down here. Mathematically, you could also say that we have phase shifted this by 90 degrees. So check this out. You've got a trough down here at the same place and time as you have a crest for the second wave. So the net result is destructive interference. But note again, we have the same waves in the sense that they have the same frequency, wavelength, wave speed. So the only difference between these two waves is that one of them has been offset by half a wavelength. We say these are out of phase, and this is a very important concept for what I'm going to be talking about today. Alright, next I want to show you an animation of something that happens. So there was research done by a guy named Young a long time ago, and what he was able to notice is that if you have waves coming in and there are two slits here, they will interfere with each other. And it turns out that you can get a strong interference down the center. Would this be constructive or destructive interference down the center? What do you think? Well, that would be constructive, right? You can tell that these waves are going to be bigger than they would be otherwise. Same is going to be for this line right here, this area, or line right here, you could say. Is there any destructive interference going on? What do you think? Well, the answer is yeah, there is destructive interference. I can see that right here, right? You can see that right here. And so those waves are kind of canceling each other out at a line. If we measured this angle, like if I had just a flat line right here and measured an angle with respect to like the horizontal or something like that, we could actually calculate these angles where you get the first major constructive interference and the first major destructive interference. This is going to be the center constructive interference, so we can't forget about that as well. So that would be like our zero order maximum. This would be the first order constructive interference right here. This would be our first order destructive interference right here. Alright, and next I want to take this and show you a diagram of the same thing. So at first it's going to be a little busy, but hang in there and I will talk you through this. So yeah, there's a lot of information on this diagram, but it's actually very, very good. One of the first things I want to mention is that it shows wave fronts that are moving in. These are parallel waves, so these would be like the crests of these waves. But it still has the idea that like a wavelength in this case would be the distance from one wave crest to the next over here, or one wave front to the next wave front over here. Alright, this D value is going to be important. That's going to be the distance between the center of this first slit and the center of the second slit. Alright, and then you have constructive interference where these wave fronts are meeting up together. They're traveling together. They're interfering with each other. It turns out you have the same thing happening over here and the same thing happening over here. And again, we can measure this angle where we have the first constructive interference, the first order maximum beyond the center one. We can measure that angle here, and that will be an important angle, or we could solve for that angle, depending on what we're trying to do. And this angle right here would be for the second order maximum right here. So that's what that gray semicircle is showing. And what do these things look like? Well, if you use something like a laser, you're going to get different patterns showing up. And so just think these two images here are just rotated 90 degrees from what I was showing you on the last slide. They would have been up and down like this. But you will get these patterns forming if you do your own double slit experiment. I've done them before with students. It's hard to set up and get it to work correctly, but when it does, it's really cool. And so you have these interference patterns form. Alright, what I would like to do is actually break this up into two parts because otherwise it's going to be too long. But I'm going to put the link to the second part in the upper right. So please take a look in the upper right and click that to watch the next lesson in the series. Thank you for listening. If you have any comments down below, please let me know, and I hope you all have a great day. Please click now for the next lesson.